Hi, Viper chemistry students. Let's take a look at this idea of electron configuration. So this is section 2 of your notes. Electron configuration, again, is giving each electron a place, okay? And so it's kind of like I've said before, it's like an address system. But no two electrons can occupy the same exact place, and so that's what chemists have developed here as a way to account for where are these electrons at in these orbitals and so forth. So as we look down through here, there's a set of rules. And this rule, the off-ball principle, basically is that electrons will occupy the lower energy levels first. Now remember that electrons pair up in orbitals. So but as they do that, then they tend to always occupy the lowest energy levels first. So there's that. This is a handy chart that you'll get used to using. So we'll kind of revisit that when you do your practicing for electron configurations. And more importantly, once you sort of get the idea of electron configurations, you can tie it to the periodic table. So then when you look at the periodic table, the electron configurations become fairly simple to figure out. Okay, and so we'll revisit this. This will be a big part of it. Now, the Hund's rule is that only one electron will occupy an orbital. In other words, before electrons pair up, they will occupy orbitals. So like, for example, there's 3 orbitals in the p sublevels. And so they will tend to occupy those individual orbitals first. So let's see if we can see a diagram like this. This is known as Hund's rule. So notice that the 1s sublevel is full, the 2s shell is full, and then there's one arrow representing one electron in each of these orbitals here before, and notice that they didn't pair up. So this would not be correct down here because it shows them paired up here. Now these little lines right here represent orbitals. So again, this is kind of what's referred to as electron configurations. Now this particular version of that is orbital notation. So there's orbital notations. Now there's another idea here. The Pauli exclusion principle just simply says that no 2 electrons could have the same address. They could not have all 4 quantum numbers the same. Okay, so in order to understand that a little bit better, we would then do what are known as orbital notations and configuration, electron configuration notation. So these are just some review. Okay, so here's the idea behind orbital notation. You use arrows. Now, on this particular slideshow, the arrows aren't lining up correctly with the lines, but if this one's not too bad here. So like if you take for consideration, here's sodium, and so we have an up arrow being, like, for example, representing an electron that has a positive spin, and then maybe the other arrow, the down arrow, as the electron spin being negative or opposite spin. Okay, so notice that the shells fill up like that, and as you go along, then you might end up having like one down here, for example, that has a single electron in it. So again, the arrows are representing electrons, and they're paired. And so, that's the idea behind orbital notation. Okay. Let's see what else here. Now, electron configuration notation is kind of like the shorthand way where you use a number, a letter, and then another number. Now, don't confuse this 2 here as being a mathematical function of squaring anything. It's just representing 2. So like this would be the 1s2, this would be the 2s2, and so forth. Okay, so those are the ideas behind notations, orbital notation, electron configuration notation. And again, this is representing an address system. Okay, all right, thank you for joining, and we'll talk to you later.